Let's take a look at some new malware uploaded to Malware Bazaar. So this has been uploaded by NDA0E. They state that this has come from what looks to be a Homebrew domain. However, it's homebrew.cx, not the legitimate brew.sh domain. And we can actually see the comparison. So brew.sh is the missing package manager for macOS or Linux. You can probably equate this to something like Yum or app, except for macOS operating systems. Now, the homebrew.ux you can see is masquerading as this domain. So they're obviously serving up some stuff, typo-squatting, and trying to see how many victims they can get. But what are they actually serving up? It is reported that this was AMOS or AMOS Stealer, which is the Atomic MacOS Stealer. So it's a stealer designed to grab credentials and other sensitive information from macOS systems. Now, if we look at the Homebrew domain, we can see that it is serving up this brew installer. So we have Intel for the x86 and x64 based operating systems, and then we have ARM64 as well. So we have both Intel and ARM based architectures that this is supported for. Now, the Homebrew domain was first reported by Sean Holo, as far as I know. Now, Atomic MacOS Stealer has been around for just over a year now. The earliest known reports that I can see is by PhD. Well, they give a little bit of a lowdown on what the Atomic MacOS Stealer is and the capabilities. It's since evolved, and the Stealer itself is trying to remain a lot more undetected than it was when the initial variants were found in the wild. So let's do some analysis on this particular sample. From a dynamic analysis standpoint, I don't actually have a copy of this in a sandbox that I can work with, so I'm going to use a tool such as VMRay. This actually gives us a nice breakdown of the process behavior. We can see that there is a bash script being used to identify the hardware type, so in particular, get some information about the system and use that in its identifier. So this system profiler with SP hardware data type. If we see something like this coming up, that's probably a good sign that this is related to some sort of malware. And we can also see the system profiler with XML also being used to get that same type of information. This is probably equivalent to your Windows version of a system info spawning and using that to identify the infected system. We can also see that the extended attributes command, the XATTR command, is being used to delete com.apple.quarantine. So this is essentially like the alternative data stream to show that something has been downloaded from the internet. So it's removing that from Brew installer so that there's not any kind of gatekeeper checks that may prevent this from running because it's removed the entirety of that. Once again, something very suspicious. We also see launchctl load, and it's loading a plist file. So it does look like this might actually be establishing persistence, essentially setting up that com.brew.brew_updater.plist file, which is going to be a launch agent that runs when the computer starts up. And then we see that OSA script coming up. Now, this is presenting a dialog to the user that says macOS needs to access system settings and is basically sitting there ready to obtain the user credentials. So this is like a prompt to say, can you authenticate? Are you allowing this to occur? And this is a way of socially engineering someone into entering their credentials so that the credential harvester can take that. Now, there's a lot of repeated prompting of that OSA script, assuming this is because this was done in a non-interactive environment. Also, this file being created that is named with a full stop at the beginning, which means it's going to be a hidden file on the endpoint. So it's likely this is being used in some way, shape, or form as well. But that seems to be it that's captured in this dynamic analysis. Now, if we actually look at the Objective-C write-up to do with Atomic Stealer, we can actually see some overlap. So where it prompts and says macOS wants to access system preferences, we can see that this is macOS needs to access system settings. Looking down in the strings, we can actually see OSA script has a prompt, which is macOS needs to access system settings. Please enter your password. So it seems like that's slightly changed now, and it's instead prompting without the please enter your password, but it still has the same pretext of macOS needs to access system settings. And we see that here in the actual execution. So there's a good chance that this is directly related. One of the tools that we can use to examine it is xmachoviewer. This was created by the same person who created Detected Easy, and we can actually open up the file and get a little bit of a lowdown on the structure of it, the segments in it, and a lot of the strings associated with it, as well as the symbols that come up in the binary. This tool is a little bit obscure and it's a little bit older, and actually there is something that's probably a little less known. If we find the file that's of interest, using Detected Easy, it has a lot of the same functionality. You might not see it here. You might see that it identifies that it's a Mach-O FAT file. You might notice that some of the visual aspects of it are very similar. And in fact, if we go to Advanced and then we click Mach-O FAT, you will see a very similar interface to what we just saw before. And that's because it seems to bundle the same capability as this other tool. This is baked within Detected Easy. So we can go and we can see the hashes associated with the segments. We can see the strings that are in this binary. We can look at the memory map. Now, usually there's a few other tools that I would use on an operating system like macOS to do some analysis. And there are disassemblers such as Hopper, also debuggers for macOS that you could use to get more information on this binary as well. But let's just take a look at it through Detected Easy at this point in time. We can see the entropy. This probably doesn't look like a packed Mach-O binary. We can use heuristic scan to see maybe Xcode was used within it. We can see that code sign was likely used to sign it. So we have the Mach-O header here as well, and this provides us some more information about the Mach-O file in itself. If we look at the sections, there is a text section, there is stubs, stub helper, constant, and a few other things such as C-string and a number of other sections in this. If we look at the string table and the symbol table, there's a few symbols in here that might be of interest, such as curl. We can see file open, get environment, get host name. We can see the creation of threads, sockets that are going on, so network connections that are going to occur. We can see data in the code. We can see the code signature as well. Now, looking over at the strings tab, there's a number of strings in here that may be of interest. We can see it's definitely associated with macOS because we can see reference to this core foundation.framework, which is used on the macOS operating system. And this is within the libraries directory, which is where we expect it to be seen. There's probably a number of strings that don't mean a lot here, or maybe they don't have any significance. There is this reference to A, which may be indicative of a buffer overflow. I don't believe it's used like that in this case, but this is a common string used in kind of exploitation that's trying to overflow a buffer to exploit a vulnerability. Like I said, I don't believe it's related to that, but something that may be of interest is those characters. And then we can see what probably looks like a base 64 alphabet. So this is used for encoding and decoding of strings. So there might be some sort of encoding that goes on in this binary. We can also see what's quite interesting. So there seems to be a list of extensions that this might be targeting. So we've got TXT, RTF, doc, docx, key, wallet, etc. So this is very interesting and something that if it came up in a binary would definitely catch your eye. Now, one of the strings in here seems to be this 7M43, etc. This is a little bit interesting because it seems to come up as a string that may be concatenated and maybe of interest, but it doesn't seem to be something logical. So maybe this is a key that's being used somewhere. So one of the things that we can actually do is take a look at this through something like Ghidra to understand how the Mach-O binary is working. But to do this, we may need to actually extract the binary because the Mach-O format actually has both the Intel and the ARM versions of the binary. So we might want to extract that. And we can do that with something like 7-zip. We can go right click, 7-zip, extract files. You can see it cannot be accessed because I'm already accessing it. Let's close this off. And it says that it cannot open the file as a Mach-O archive. That's all right, because in this, we can see that it has actually extracted ARM64 and x64 as the files. So using Ghidra, what I'm going to do is I'm going to open up the Mach-O binary of interest. So in this case, I'm going to use the x64. And we can see that Ghidra's actually identified that this is little endian based, and it is actually compiled through GCC. We have probably the language that needs to be used to interpret this properly. So let's just go OK, and we might notice a few errors, and that's because there are some symbols that may be unknown in this binary. That's okay, let's just click OK. So what we're going to do is we're going to open this up in Ghidra, and we're going to ask it to be analyzed. We're probably going to leave the defaults on and just hit analyze. So it doesn't take too long, and we can see that the analysis has finished. Now, if we look at the defined strings, this is similar to what we saw before when we were looking at the binary. So we can see that 7.4 string mentioned here. So what I'm going to do is actually just go into it and try to delve into this a bit further. So if we take a look at where this string is used, it seems like it's used in a number of functions. If we go to the first cross-reference of this, so just click on this function, it looks like that string is being used in a XOR operation, so that's what this caret symbol is indicative of. And then there is also a modulo operation, so that's what this percent symbol is indicative of. Now, if I was to look at how this seems to be in a graph, I can actually see that there is operations that occur in a looping fashion. So this is telling me that the bytes are having these operations occur over them to change their contents in some way, shape, or form. I really want to understand what is being passed to this particular function. The reason is because we can see that it takes two parameters, parameter 1 and parameter 2. And for parameter 1, it's going to take the bytes for that, and it's going to then do that XOR operation and then have the modulo operation occur on it with 0x1b as the key. So let's dive into this a little bit further and see how we can recreate this. I'm going to create probably a Python script to do this because it'll be quite simple. So I've started a Python script, and the first thing I want to do is define the encryption key that we know is going to be used. Now what I want to do is probably create a placeholder. So for encrypted bytes, we're just going to specify this as nothing yet because we don't know what the encrypted bytes are that are being passed to this function. Now I'm going to do probably decrypted bytes, and for this I'm going to give it a byte array and probably just give it a size of, I don't know, maybe 100, depending on how big the strings are that are being passed to it. We can just kind of use that as a placeholder. Now I'm going to define a function, and I'm probably just going to call it decrypt, and this is going to take in probably bytes is what I'm going to specify. Now for this I'm going to create a for loop, and we're going to do this in the range of the length of the encrypted bytes, so that all of the bytes are going to be combed over with this operation to ensure that they're all decrypted. Now I'm probably going to recreate what we had in the code browser, so I might just take this as a bit of a referral so I don't forget what we're creating here. So what I'm going to do here is try to recreate this particular operation that's occurring. We know that the bytes are going to have this occur over them, so we are going to pump this out to the decrypted bytes. So I wanted to find the decrypted bytes. Now in this case we can see that it's parameter 1. Now parameter 1 is going to be essentially the bytes that are passed to this function. We can see that they're specified as bytes here. So this uvar1 is increasing every time, so uvar1 equals uvar1 plus 1. This is telling us that this is a for loop, so that is literally only being used to facilitate the for loop. Now because we've actually got a for loop here for this for I in range, we actually don't need that. So it'll probably look more like this. So we want to have the bytes, and we're going to have to specify the one that's being used. So the first bytes in the range, we are going to have this operation with the encryption key. In this case, the encryption key we can see here. So we've recreated that, and that uvar1 was just for the for loop. So this is going to be I. So we're going to do I. We're going to do modulo and 0x1b. Now we've essentially recreated that operation. I'm not sure 100% if there's going to be any issues here. Let's just try and actually see what we get. So I'm going to have to return for the decrypted bytes, and then I'm probably going to do a print statement to say I want the decrypt function to be run against the encrypted bytes. Now, if we get some encrypted bytes, this ideally should work, but we should take a look back at our code to figure out where that's happening. So we do have parameter 1 and parameter 2 being passed this function. Let's take a look at what calls this. On the left-hand side, we can see quite a lot do call this. So looking at the first one, it does seem like maybe this string is being passed to it, local 470. So it does seem to be that string here. So that's a bit interesting because straight after that we have that run. So ideally we should be able to use this as byte string. To get this, we could actually take this, right click and go copy Python byte string. If you haven't used that before, you will have to go copy special and then click on Python byte string and paste this in. Now, if I was to run this script, we can see that there's an error. And that's because the operand types here that we're specifying is both an integer and a string. Now, to fix that, all we'd have to do is specify that this is an ordinal, pass it to an ordinal when the operation occurs. And we can see that now that has come out as the number 76. So if I look at the calls to this method, there does seem to be a few functions. There is a function now of A37. And if I was to examine that, I can actually see that local_AE is the parameter that's being passed to it. And we have this DAT that's being moved into that local variable. Now, if I was to examine that, I can actually see that this seems to be a data stream that probably doesn't make a lot of sense. So what I'm going to do is I'm actually going to take all of this all the way up to the end of the definition and right click and use that copy special, and we can go a Python byte string is really what we want. So if I copy it as a Python byte string, I can now go over to my script, paste it in and run it. And we can see that now the number 77 has come up. And it's at this point I've just realized what I've done. I'm going to go back. The reason why 76 came out before is because I'm actually only specifying one byte here that's being returned, not the actual array. I need to change that to include the array. Silly error on my behalf. Now the null values are because I've given it an arbitrary length of 100, but outside of that there is this A46L. Probably in itself doesn't make a lot of sense, but let's see what happens if we actually paste in this new byte stream. So now if I run with the new byte stream, I actually haven't given it a large enough size. I could make this 150. I'm not sure how many characters are actually in this. And now we can actually see a lot more. I think for the sake of defining a byte stream and making it dynamic, I might just make this the length of the encoded bytes. And that way we shouldn't have any issues going forward. So now if we actually run this, we can see OSA script is being run, and I could actually decode this as, UTF-8, we'll leave that by default. And now if I run it, we can see a little bit more clearly that there's an OSA script being defined saying tell application finder, move POS6 file, one file to another with replacing, and then ntell. So this looks like Apple script that's being run to tell the Finder application to move one file to another location. A little bit interesting. Let's see what else we can find in these strings. So we could go back once again, find the next function, and it seems like there is a pretty clear string that's being defined to this one. So what I might want to do is actually find where that string is defined. And now copy out all of this. I'm not sure if it includes this data down here, so I might just take the whole lot, given they're not really new definitions, and once again copy that Python byte string. Now if I was to replace the encoded bytes, because we've copied the byte string, we can once again just replace this with a new one and run it. And you can see once again there seems to be that mention of OSA script, tell finder this. So once again, seems to be something to do with an OSA script that the strings have been encrypted using this method. So when we're looking at cross-references to our decoding function, so in this case, this function, I'm first just going to rename it. So we can just call this function decrypt. Now we can actually see where this is used. Looking at the incoming references to that decryption function, there's actually quite a lot that's having their strings decrypted. So we could go through each of these functions, figure out what strings being passed to it, and do the decryption using our new script. One of the interesting things about this version of AMOS Stealer is where we see the decryption key, we can see it here as this 7M. If we scroll up just a little bit, there are a number of strings that almost seem like they are encrypted, and so we can actually leverage this to unveil some of the strings that are meant to be in this binary. Now there's quite a lot of these, unfortunately, but we can still, for example, take, let's say, the first one here and copy the byte string, and if we make this the encrypted bytes, we can now see that it comes out as system.txt. And we can go through and do this for pretty much all of them. So we've got base CFG, and what seems to be formatting strings. These strings are currently being found in the C string section of the Mach-O binary, but there are some others that are sitting in the const section, so we can see that that is the one with all the A's and some of those other strings associated with the OSA script that we saw before. And so by going through the strings of this binary and decrypting them, shortly after we see this reference to home, we actually have this string that starts with 9 at CW. And if we copy that into our script and run it, we can actually see that it comes out with 85.217.222.185 static.php. So now we actually have the command and control associated with this malware. So I've gone ahead and painstakingly extracted all of what appears to be encrypted strings in that binary, and I've put them in an array, and then I just added an iteration over that array. So you can see that there's enc bytes array. For each of these, I get the length and then I decrypt them. And now if we run this across our binary, we can actually see a lot of what is actually involved in this binary. The mystery begins to unveil itself. So we can see that there's alias files. I will mention probably the last character in all of these is going to be a dud character, perhaps, or something that isn't actually right, and that's because of the null bytes at the end of these. But that's all right. We can see alias file, startup disk mentioned, we can see launch agents, we can see brew updater, we can see that launch CTL load, and that string before that is likely going to be passed to it, so that's going to be the launch agent being mentioned. We can see evidence of it deleting files, we can see the C2, we can see that the content encoding for the C2 is being specified as binary, we can see that OSA script is setting the volume output muted values, we can see this pw.dat, so perhaps a password file being mentioned, we can see getting rid of the extended attributes that we saw, we can see an identifier, a GUID identifier as well, we can see user agents, we can see mention of a screen capture, the system profiler to get the hardware information, we can see ps-awks for understanding what processes are running on the system, we can see login data, we can see extensions, we can see preference files, cookies, SQLite, so all associated with stealing session cookies or logon data from browsers, we can see FTP, FileZilla, recent servers, more cookie stuff, and the list goes on. We can see evidence of crypto wallets, Discord tokens, Wasabi wallets, Exodus, Opera, Mozilla Firefox, Google Chrome, and we can see that duplicate file that we saw before. This looks like it's actually prompting and saying that there was an execution error when you try to run the binary as a bit of a way of making the user unaware that they have actually run this credential stealer. But that's it. That's what I wanted to show you today. Thanks so much for hanging in there. Let me know your thoughts, feelings, comments, anything else in the comment section below. If you found it useful, let me know. Give us a like, subscribe if you feel like it. They're free. They don't cost you anything. And this video is free. It also didn't cost you anything. So it would be appreciated as it does help the algorithm and it does help get this educational material out there. So thanks so much and I will catch you next time.